Okay, so I can start now. And thank you very much for coming again. So some just basic points, and I want. Okay, so let me just say the points here. So first, we kind of had a problem with recording the first session, so I hope that we can solve it from now on. This is the first thing. The second is that whenever you want, just please interrupt me. So I'm in no rush to finish everything. And also for the online people, so because you may write in chat, but we cannot see it, I guess, in a practical sense. So just open up your microphone and ask it loud. So yeah, I guess it cannot bother us that much. And so I guess that's it, huh? And our video is kind of, it tends to be blurry. So for the online people, if you find it blurry, just again, shout it out so that we know it. And let me begin with a quick recap.
Yes.
Yes. Yes, yes, yes. Yes. Yeah, yes, we are recording here and on my computer, but not on that computer. So yes, this is the reason that you can see. That's very good. Thanks. But there, right? Yeah.
I think it's better for people to talk.
Yes, but still, maybe it's good to have also the chat open. Thanks. Okay, so I want to move to the first board. So please, yeah. Okay, so let me start with a quick recap. We defined what a category is, just objects, morphisms, you have composition, identity, blah, blah. And we saw some examples of them, and a preorder, so a set with a transitive reflexive relation. That was one example. So one object and one monoid as the morphism over that one object is another one. And the one that we are really interested in is sets with functions as the morphisms, and actually three other set-like things. One was this, and I also want to call it set to two for some reasons that we will see later. And the objects, if you remember, were variable sets. Technically, an object is just one function from one set to the other. And my interpretation is that it is a set that varies over time, and time means 2 points, just 0 and 1. So you have a set here and there, and this is the function that records the evolve of any element. It's not necessarily surjective, so you can create things afterwards. It's not injective, so you can just find out that things are equal actually afterwards. So what are the morphisms? We saw that morphisms are, so if it is another object, so they are pair of functions such that this guy is commutative. And we had another one, fix some group G. We had set to G. So the objects were write G actions that I won't define again. But technically, any element in G acts as some bijection over X, right? And what are the maps? The maps are just maps between the sets such that they respect the action of G, right? So they are equivariant functions. And finally, we had this guy, So we didn't have any name for that. So let's call it quivers. So the objects are just directed multigraphs or quivers, something like this. And so maps are just the obvious maps between these graphs, right? So, and we saw something about injective functions in a categorical setting, construction of categories from categories, opposite of a category, product of a category, blah, blah. Okay. So now what we are going to do today. So first, I want to say that what's our goal, the immediate goal is that I want to define what a topos is, right? And roughly speaking, a topos is a category with some structure such that it is just really, really, really close to this guy in behavior, right? It's that close, it's not equal or isomorphic or just the same thing, but it is just with same behavior such that you can pretend that you are actually working with some sort of generalized sets, new sets, right? And so my strategy is just the following. So I pick this guy and I pick some of its structures or properties, and they may seem kind of random. And then we try to write them down in the categorical language so that we can use it as axiom for toposes later, right? So that's the strategy. And so before going further, maybe I have to say something more. So when I define toposes, then you can see that this guy is a topos, this guy is a topos, that guy is a topos. So you can pretend the G action is a set actually, or a graph is a set in some sense, or a set that varies over time is a set. So you have different notions of sets. And of course, then you can use it to prove independence because you have different models. So you can use them for independence. But I have to emphasize that they are not, toposes are not, they are natural objects, right? So the situation is not like that you provide some sort of weird, very tricky models to prove independence. The situation is like non-Euclidean geometry, if you like, right? So it's not just that we want to prove that, I don't know, the parallel postulate is just independent. The thing is that there are real geometries out there where you have curvature, and then the geometry of these guys is actually the non-Euclidean geometry. So a similar thing happens here. There are real natural notions of sets, alternative sets out there in the world, right? We can use it, by the way, for independence, but they are more important than just independent, right? Okay, so let me start just with the first of all structures, right? So the first of all is this. So as I said, you may feel that they are kind of random, right? There is some coherence into it, but just bear with me. One, in set, this guy, you have a singleton, right? A singleton. What is the categorical definition of singleton? What's the property just based on morphisms, composition, identity, these things that characterizes a singleton?
Hi, sorry. What should we do if the video is blurry? Should we jump?
Exactly this, thank you.
Okay, good.
So
Thanks.
is it blurry really?
Not extremely blurry, but it's blurrier than before.
So maybe you can change it and come.
Is it just me, my video?
Okay. So do you have any idea? Yes, but you know that that's cheating. You have an idea. From each to itself. Okay, that's not bad. So the idea is that the guy is characterized by the property that there is only exactly one morphism from itself, from the guy to itself. Yes, but this is also true for empty. That's bad. It does not characterize. but you have actually halfway there, right? So actually from anything to it, there is exactly one morphism, right? Singleton has this property that from any set, there is just one function into it. Exactly one, right? And this is a categorical property. You can say that for any object X, right? So say the object C is your singleton, such that for any X, there exists exactly one morphism, say F from X to C, right? That is at least the property that the singleton has. And that's a reasonable property in the sense that if something in any category has this property, it is unique up to isomorphism, because otherwise it is not a reasonable definition, right? When I can say that I'm defining something, that I have actually the uniqueness of the guy, and this guy is unique. And how do I know that? So let's say I have also another D with the same property. And of course, then you have a map from C to D, because D has the property. One map from D to C, because C has the property. And then what? And the compose, you have a map from C to C, but there is just one map from C to C by this property, and that is identity. So the composition is identity, and the other composition for the same reason is identity. So these guys are isomorphic. So that is kind of the main idea that I won't repeat again and again, that you define something in this universal manner, that for anything there is a map and there is a unique map, or you have that property. We will see some examples. You have some property, then this guy provides that property, and it is unique in the sense it is the greatest in some sense, it is the least in some sense, and that some sense is that you can factor any other thing via a unique map. And then via this property that people call universality, you can prove that it is unique up to isomorphism. Okay, so forget about this thing. This is something, some categorical definition, and people call it a terminal object for obvious reasons, because it is just the end of all objects. There is a map from anything to it. There is a dual version that's called the initial element, meaning that for any X, there is exactly one map from C to X. And instead, the initial is empty. Exactly. So I also defined the empty. So, okay. Also, of course, by duality, it is unique up to isomorphism, right? So, exactly. So we have terminals, initials, and we know that they capture kind of the singleton set, the empty set. That's good. So before going to second guy, so this is kind of the structure, the very obvious structure that I want in any topos. But I want to go to talk about some philosophical kind of thing before going further. And that philosophical thing is that in category theory, when you have a category, you have no information other than the morph, right, between the object, right? The definition of the initial object? Yes. So C is an initial object if for any other object X, there exists exactly one morphism from C into it. Because first from empty, you have just one morphism to anything, and that's just the empty function. And of course, it is just the only thing that you have this property. Okay. So the philosophical thing is this. So when you have a category, everything is relative. That's the beauty of it, right? And you understand some object, right? Just by looking into the morphisms to this guy or from this guy, right? This is the only information that you have, really. So, and these are two different approaches. So one is that you always fix your x, say, right? And then the first approach is that I just investigate all the morphisms from some or all, I don't know, from some test objects, say. So I have some objects in my category. I consider them as easy, simple, you know, easy to handle, whatever, right? And then I investigate X by the maps from that guy or those guys into X, right? For instance, in set, we usually pick this set of all objects, some objects, as just one, the singleton. By the way, so this guy is unique up to isomorphism, so it deserves a name, right? The name is one. The terminal object is one. The initial is zero, right? That's the name for them, of course, up to isomorphism. There are many ones, but up to isomorphism, there is just one. So here, all the singletons are one, but kind of there's just one up to isomorphism, right? So instead, we love our one, the singleton, because we can understand a set for all the maps from 1 to x, right? And these guys are the elements of x, right? So these are the elements of x. I understand a set by the elements of x. And actually, this is true for sets, that x can be really characterized by all the morphisms from 1 to x, by all its elements. That is not generally true for my weird notions of sets, like the sets, the variable sets, for instance, right? We will see that. Or what else? Or for instance, when you are in topological spaces, so you have a topological space, you fix I as just 0, 1 interval, and then you investigate your x by all the continuous maps, by all the paths, right? That is a known way to investigate x. This guy is a test space. It's just kind of easy in some sense. And you look for all the I-shaped things in x, if you like. And in here, you can say that I'm investigating T-shaped things in x, right? So some parts of x, not just elements, it can be some parts even, right? And there's a dual thing. The dual thing is that you investigate the guy x by the map outside of it to, say, some test space, right? So for instance, again, instead you do this. What should I put here? Two, exactly. So you can investigate x by the maps to 2, and these are just a subset, right? These are the characteristic functions. These are the subsets. You understand sets by the subset. You do the same in topology, for instance, by investigating x by all continuous functions to R, right? Or C, or the real valued things, right? So these are the T shapes. These are the T values, right? And both of, and okay, so say if I pick some small amount of T's, and if I characterize the whole information next in the map from T or some T to the guy, then I'm in a good situation because I can kind of open up X, you know, to parts or to different valuations on it, right? So these guys, okay, let me put it here. So if your category has 1, and it is possible that you don't have 1, right? It's possible that the category has no 1. Like if you have a poset without any bound, you have no initial, no terminal. So these structures are not given. So sometimes they exist, sometimes they not. So if you have your 1, then any map from 1 to object X is called the element or global element. And the global comes from geometry. So you have the global sections, etc. Right? You have the global element, and or the point of x, if you like. And these guys are not enough to understand x in any category. So in sets, it is the case, but not usually. So for instance, if I have set variable, right? Then the maps from, okay, what's one? What's one here? First. So the good thing is that whatever I talk about today, all of them are component-wise defined. So you can see that one, you can check it, but one here is just singleton, the obvious map. So it's just that. Or if you want up to isomorphism, it is just the constant singleton. So then if I have A0, A1, this is my object X, and I have singleton, right? So a map from 1 to X is just this guy, right? I pick one element here, one element there, such that this element is mapped to that element, right? Because this guy should become committed. So therefore, the data here is just redundant, right? So the only thing is just one element here. So maps from 1 to X in this category are in one-to-one correspondence with the element of the 0 set. So if I have something, because this guy is evolved, something added here, right? Then I cannot see via the morph, right? The global elements are the static elements, the elements that are here and changes over time, of course, but you cannot see the new guy. What do you mean? So yeah, the objects are just functions between two sets. But the idea is that the function maps the elements here to their correspondence in the future. But of course, you can have something more. Yes. Exactly. This is my X. My 1 is this guy. And then this map is just these two, such that this guy is commutative. And the whole data is just one element here. Right? Okay. So the same also one element A1. What? I don't get it. So yes. No, I don't want to define it. I want to understand it, right? So I have my 1, I have my guy, and then I'm thinking that, okay, what is a map from 1 to this guy? It is just one map here, one map there, meaning two elements, picking up two elements, such that this maps this guy to that guy. So therefore, I have already this. It is just the image of this. So then the whole data is actually one node here. Or if you like, two nodes, such that this guy goes to that guy, right? Yes, yes, something in the image, if you like, but not really, no, because then it is possible that two things go to one, right? So I can find this guy from this guy in a unique way, but not the other way around. So therefore, it's just meaningful to pick this. Okay, so you cannot have all the information, right? The global elements, just the static elements. The same happens, I want to explain for that set to the G guy. The set to the G guy, 1 is exactly, again, singleton with the action, and the action should be just obvious, right? It is just singleton, right? G maps star, whatever. And then if you have another action, then the map, right? These guys here, they would be what? They would be functions that are equivariant, right? That respect the action. So meaning that I'm picking an element in X such that it is a fixed point for any X, right? Any G, sorry. So the global elements are just the invariant elements. And of course, you cannot understand action with invariant, right? You're killing the dynamism, it's static. Yes. 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 Yes, it is an action, but the action should be trivial because it's a singleton, so you cannot. G times star is star. You cannot do anything. Yes, it can be anything. Yeah. Yes. I write star because I don't care about the name and I want it to be unique, right? Kind of. What's this picture? So, okay, so you want to go to this category set to the G, right? And understand this situation. So first, what is one? One is a star with the obvious action, right? Is it fine? An obvious action is just a function from star times G to star, but there's just one function there. No. Sorry. No. Or yes. Yes, but yeah, technically this guy comes with an action, right? So I write just a set, but the whole data is actually X and dot. Dot is the action. Here I have star and dot is the action, right? Dot star, say dot X. And the map between the two is just a function between the sets of it. So meaning just picking an element X, such that it respects the actions. And respecting the action means that f of anything after applying G to it is f of applying G to it. Is it? No. Yes, I can write it in more detail like that. Yeah, we can, and then we have. So if you change my board, then I can do it. So, okay. So first, what is a guy here? So an object, if I want to be precise, is something like this, right? And this guy is just a function with some properties. That's an action, right? And what are the morphisms? The morphisms, if you have two of these guys, right? What is a morphism? A morphism is a function from X to Y such that it is equivariant, meaning that for any G from the group, f of G dot X equals to f, okay, sorry, it's right. So this right? So I'm respecting the action. So now with this data, first one is simply the singleton with some star, some action, but the action would be what? Would be a map from, say, star times G to star, and there is just one function. So everything just is invariant. And then you pick some X with its action, and then what is the global element? The global element from, okay, so from one, which is this. Yes. We have, okay, so if I say the global element, then that's wrong. So it should be global element. So then the global elements of my x and star, right? So let's say this, right? Then they are functions from this to x with this property, right? This should be equivalent because we are talking about morph, and morph f is a function from the first to the first. Yes, which is an element in x. So let's say that is f. So you have f of star, an element of x. So then I'm simply picking one element, but not any element. You should have this property. And if I write this property, it would be what? It would be f star dot g is f star dot g, right? But star, yeah. So then it is just invariant. Exactly. So then I have what? So I can pick any element actually in X as f star, as long as it is just invariant under any action of G, right? It's a fixed point of G. Because this is the only condition that I wanted. So, and so of course, then you cannot here. So, so the point is that of course, then I cannot understand an action, right, based on just the fixed point. Of course. So if G is interesting, right, so then that's not the answer. Or the action is kind of trivial, right? It can be just all the, but in general, you cannot do that, right? So you are missing some dynamism. This is the whole idea. Toposes versus sets is dynamism versus static, right? If you have sets, dynamic in some sense, meaning growing over time, or having some action as some sort of transformations over them, these are toposes. So toposes are variable sets, if you like, right? And then of course you can have it here and there in geometry because above is straight, right? So then what? Maybe okay, anyway. So I won't explain, but in Quiver, right? One is just what? Is again point y. One edge, one node, right? Therefore, it would be what? It would be a loop, right? One edge, one node, two source and target. It's just a loop. Global elements are loops in a graph. You cannot understand the graph by loops, right? So, okay, that's it. And then I have kind of explained that global elements are not good enough. But then people say that, okay, maybe it is just reasonable to work with all maps, with all y, sometimes with some specific y. And these are called generalized elements, simply because, yes, they are elements of X parameterized with Y, right? So in logic, you say that these are closed terms, and these are just terms. And we can even know that we cannot understand the whole term by closed terms. Okay, so then what? So also that guy is also important, right? Understanding the thing by its parts, even in toposes. We will come back to this guy later. So the whole thing is around 0 and 1, the initial and the terminal. So the second guy is the Cartesian product of two sets, right? So sets have the property that we can construct the Cartesian product, right? It's closed under Cartesian product. How to characterize this guy in a pure categorical language? Any idea? If you know it, you know it. If you don't know it, then that's fun to find it out. Let me help. So let's say that I have two sets, right? Then what is the Cartesian product? Whatever it is, it's a set. So therefore, I have an object. This is the set of all Cartesian products. The whole Cartesian product, the set of all pairs, right? It also interacts with A and B because it is the set of all pairs. So you have projection. This is what, the connection between C and A and B. So you have projection. Say P0, P1, P1, P2, whatever, I don't know, right? Then what? That's not enough. Of course, it's not enough. Why? Because let's say that C is the Cartesian product. You have this data. But C is any subset of the Cartesian product. You have also the same structure. You want this structure the greatest possible one, right? Because not just the subset, the whole thing. You want something of that sort, but the greatest of them. Meaning that you want to say that this guy, together with the projections, is actually the Cartesian product if for any other D such that you have two functions to A and B, you can construct the pairing function here. And this guy is unique, right? So again, you have two objects. What is the product of them? First, it is not one object. It is one object with two projections. This is the whole data. Such that it is the greatest, meaning that if I find another one, you can factor it in a unique way, right? Yes, so I mean, there is one morphism such that these triangles commute, so I'm factoring, and it is unique with this property of factor, right? So it is similar to that terminal thing, right? In terminal, I'm saying that the guy is terminal when it is terminal, meaning that from anything else, there is exactly one morphism to it. Here I'm saying that this cone is terminal. There is a cone, and this guy is terminal, meaning that for any other cone, you can factor it in a unique way, right? If you write it down, you can see that it really characterizes the product in Z. And again, with that sort of argument, you can see that it's just unique up to isomorphism. So it deserves a name. The name is A times B. You can dualize the game, right? To say that I have A, I have B. Maybe there is a C such that there is two morphisms into it, two functions into it. And this is the least possible one. Meaning that for any other D with these two, there exists exactly one factoring like this, right? I'm just dualizing the above one. Yeah? No? That's a very good question. So in my presentation, it seems that they are the same. Technically, it's not, because having something and one cone over it, the formal version of it, then it is important that A is first, B is the second. But here it seems it's not. But really, they are different, but they are isomorphic. So. No, because they are isomorphic, as I'm saying. A times B, B times A, they are isomorphic. So this guy, right? I'm dualizing things. What is this guy in set? A set with two maps from A and B such that it is the least, say, co-cone. What is it? Decision unit. Yes. It simply says that, okay, put A, put B together somewhere, and nothing else, because it is just the least. Right? So again, unique, deserve a name. A plus B, and these two guys are the I0, I1. Sometimes people call it. Okay, so that's good. Of course, if you apply it in posets, you get meet and join, right? The least upper bound and greatest lower bound. Sure. Both are small.
Singleton is the biggest that which does
Yes.
nothing, or
This is my abuse of language, but it is kind of intentional. The thing is that I want to say that so here, for instance, your C is biggest in some vague way that it is the end of all the functions. So everything goes there, right? In that sense, it is the biggest, but not in the sense of size, in the sense of the order, if you like, right? But again, of course, the unique morphism is also important. So I'm using the language, right? Okay. So, okay, I have these two guys. I love also these two guys. I want them, sure. I want them to have in also process. Up to isomorph. Yeah, the whole data actually is unique in the sense that if I find another D and another cone with the same property, then there is an isomorphism here such that these guys commute, right? So then the cone is unique, kind of. And okay, so these are also structures that I want. What else? How to compute these guys in my example? Point one, always point one, right? So you have two, say, variable sets, right? Two variable sets. You want to add them up. Just add these guys, and use the obvious mode, right? Just do the obvious thing. I want to explain, but everything is just point one. Okay. So the next thing that I want to say is that now I know how to produce the product of objects. What about morphism? Right? Because usually when I have set A, set B, set C, set D, and two functions, right? So from this data, you can construct a function that we write like this. Okay, that's misleading, but let's say this. That reads a pair and computes F on the first, G on the second, right? Always we have this instead. So is it possible to have the same, say, in any category? And the answer is yes, of course, right? How? So how to go from A, B to A? You go with projection. Then you go to C and D with F and G. So now from this guy, I have a map to C and to D. And of course, then I can construct a map to say C times D such that this guy, these guys commute, right? And then that map is called, say, F I. There is a canonical map. If you compute it instead, then you see that it is just the usual map that we have. The same also happens here, right? For plus. Okay. So, what should I do then? These are all good things. Okay, the next. The next guy is a way to construct subsets subsets. How to construct subsets? So in set theory, you construct your subsets by what? By separation, right? You have a set, you have a property, then you pick separate that one, right? Here we do it, at least the minimum way of it is this. So you have X to map to Y, right? And what I want is just the sub part of X, subset of X, that equalizes F and G, right? So usually you have two functions, right, instead, and you can just pick the element of X such that F and G are equal. What is the categorical version of it? It's a subset of X. There is a map to X then, right? Such that these two compositions are equal because it equalizes, right? But it is the best, the greatest in some sense, right? Because that cannot capture the whole thing. Any subset of it has that property. It's the best. The best means that for any, say, W, yes, such that you have the equalizing thing, then there is exactly one morphism from W to Z, such that you have. But yeah, even if they are all subsets, they are the whole subset, right? All of the subsets. And then here you want to construct subsets from two given things, right? So here I'm saying kind of that you have atomic separation, because it is just the set of all things such that f of x. So it is x in x such that f of x equals to g of x, right? So that is just very basic, say. Let's say that you have equality just in the language, then what? Then it is just the basic separation that you get, right? Okay, the guy is unique, blah blah.
Sorry, it would be possible to move the camera? Thanks.
Okay. So I was saying that if you have two maps, F and G from X to Y, then the set that equalizes these two, let's say a subset of X consisting of things like this, is just a map to X, such that it is just the greatest, meaning that for any other guy, any other map, such that they equalizes F and G, then you can factor it uniquely, right? Okay, but let's do an exercise. An object. I won't say that it is a sub-object, meaning that it is monic. The only thing that I'm saying is that the whole data is Z, one object, one morphism to X. This is the equalizer of these two. Z and this map together. So like there, so you had product, the guy with two maps, guy with one map, right? So now you expect this guy to be a subset really. And the formalization of subset is monic, right? So what is a monic map? We talked about that last time, but a map X to Y is monic if, and it is the categorical version of injective, if for any two other maps, if the composition, say, so this is your F, if it is G and H, if FG equals to FH, then G equals to H for any GH, right? That is the obvious candidate for injective. And monic characterizes, monomorphisms characterizes subsets in a meaningful way, right? So if it is a subset, it should be a monomorphism. Let's see if it is. So Let's write the big guy here. Two maps, FG. Let's say that the equalizer exists. Let's say that it is E, right? My claim is that this guy must be harmonic, right? Let's prove it. So let's say that I have two maps, say, I don't know, I and J, such that EI and EJ are equal, right? And I want to show that I and J are equal. How to do it? The only information that I have is that this composition equalize 1, 2, that's the best. Meaning that for any other guy that equalizes this, there's a unique factorization. Like this. Use this information to show that these two guys are equal if EI and EJ are equal. It could be a nightmare working with arrows, right? But it's not that hard. So, say, first, FE and GE are equal, right? And EI and EJ are also equal. So you have a map here that is just a map EI equals to EJ, right? And FG composed with this map are equal. Why? Because these two are equal and then these compositions. Okay, so now you have a map equalizing these two. There should be a unique factorization along this. So these two should be equal. It's a unique factor, right? So just exercise to see how I'm using universality. But the thing is that this guy, when it is equalizer, when I have my atomic separation, then it really defines a subset. So it's kind of consistency check that I define monomorphisms as my subsets. This is my kind of very basic separation. So there should be some consistency check. Okay. Yes. And the last guy, between all the, yes, there is a dual version. There is always a dual version, right? No. So when you talk about uniqueness, okay, Z is fixed. It says that for any W, for any map that equalizes, there is a map. And that map is, there is a map that commutes this. And that map is unique, meaning that for any W, if you have, but Z is fixed, for any two maps, such that blah. Yes, depending on X, you have. So what do you mean? If you have X, then you have a subset, right? It is possible to have, but this subset is unique up to isomorphism. So I can change the names and yeah, exactly. That's a very good thing. So let's say that I say that this guy is unique up to isomorphism. So meaning that if you have some E prime and Z prime with the same property, then there is one morphism between them such that it is an isomorphism. So these guys are unique up to isomorphism. And that isomorphism maps E to E prime. Yes. So therefore, this morphism is allowed. Okay. What is isomorphism again? A map from X to Y, right, is called isomorphism if it has an inverse, right? So meaning that there is a G such that FG, GF are identical. So one map could be an isomorphism. So then if I say that I have z prime and I say that it is unique up to isomorphism, it means that there is an isomorphism between them. That is meaningful. What is not meaningful, obviously, is that what if I have some morphism as well? Let's say that there is some x and two morphisms, and I say that this data, guy and the morphism, is unique up to isomorphism. What does it mean? It means that there is isomorphism between the object part commuting with the map.
I think when you were saying you need
No. Always everything is local. Yes, if you do it isomorphically. Because everything is about morphisms and isomorphisms. Things are the same, right? I don't care about the names. So I have my set theory where I don't care about the name,
big arm.
right? Yes. Yeah. True. Exactly. How do I know that? It is kind of similar to what you know in group theory, right? So you have some groups, you prove something about the group, and you know that you use everything in a correct way, such that if you replace it with another isomorphic group, it's also true there. I'm doing the same thing, right? But kind of. That's hard because good groups are not good really to capture that. I see your point, but let's say that they are groups. And let's say that I'm proving something about some group in the category of groups. And you're saying that, okay, I can change this group with an isomorphic group. And I would say that, okay, that's again fine. Because I'm kind of aware that what I'm doing and everything that I'm doing should be up to isomorphic.
You do have expression of the top line movement, so you have to be very careful about what.
I'm not saying that I have extensionality really, right? I'm saying that I have some separation, some very baby separation up to item, right? Okay, so you have the dual, always you have the dual. And the dual is what? The dual is this. The dual is that you have two morphisms, you want to equalize them, but by composing on the other side, right? So how to do that? You have two morphisms, say xy, again, fg. There exists some z, some say phi, or p, why not? Such that pf and pg are equal, and p is the best, meaning that it is the least in this case, such that for any w, for any other guy, such that you equalize these two, there exists one map from z to that, because z is the least, such that, you know, what is the theoretically discussed? That guy was separation. What is it? What's the dual weird guy? It says that I'm working with y, but I'm gluing any f of x to g of x, right? There's some quotient here, right? On some equivalence relation. And I'm claiming that z is actually y over this relation. And this relation is generated, not the same. It is just generated by this relation for any x. Let's say that f of x should be equal to g of x, right? So I'm gluing f of x to g of x. because I want to pretend that F and G after the composition are the same thing. So if it is just the projection of some equivalence relation, I have to pretend that F of X and G of X are the same, but I have to do nothing more, meaning that the relation should be generated really by this guy, nothing more, right? So you can check instead that actually this is that, Z is just Y over this, the equivalence relation generated by this guy, and pi is just a projection, meaning that Y goes to the class of Y. Okay? So if that is separating a relation, an obvious relation R, this is quotienting over an obvious relation R. Right? I have my quotient, and this is crucial in any set theory, right? That you have to be able to do your quotient. Sure. You mean what, for instance?
So like, well, I should be to just any.
Mm,
Doesn't,
no.
or only some relations that you've been like.
Generated by this. No, no, no. It depends on your structure, of course, but no. No, like that. So I'm not saying that that separation implies all separations all the time, right? That is just some specific separation that I have. You need more, you have to add more, right? We are kind of inspired by that. We bring out some structures, and then we axiomatize our topos by these, right? So let's say that I'm working from now on with the categories, with products, co-products, and equalizers, right? Then it means that I have that separation in my small baby set theory, but nothing more really. Or anything else that you can construct with products, with, I don't know, you know? Yes.
Then I get like zero separation.
True, but your set is kind of fixed, right? It does not mean really anything.
Which is
The category of sets is fixed. It's just one example, right? You're saying that in your example, this is true, this is true.
according to the ratio.
That's true. That's true. Yes. But there in your argument, you use some kind of notion that's called sub-object classifier that I will explain, right? So, okay, you have your quotient, and now I need the last universal thing. So, the last thing, so what is it? That was 2, it's 3, it's 4. Right? The last construction that I need for now is the following. So if you have a subset, so let's say that I have a move, I have a function, and I have a subset, right? Formally a monique, right? So one of the constructions that I have in set theory is just constructing the inverse image, right? You can compute f minus 1 of u as a subset of x. How to characterize it in a categorical way? Of course, it is a subset. To say that it is 3 is a subset, such that if induce a map here and this, then this guy is commutative. I'm simply saying that if you go using f on v, you end up in u, right? But of course, it's not characterized the f minus 1 of u, the inverse image, because simply I'm saying that f of v is a subset of u. But v must be the biggest possible one, again, the greatest, meaning what? Meaning that if I have some w here, two maps, some other corner, then there is a unique map here, right? It is the greatest. Okay. Yeah. That's the meaning only. But in general, there is no need to have a monic really, right? It's also useful if you have just some map, anything, right? And it can be some other map and some, I don't know, right? So this guy is called a pullback for obvious reasons. So the whole information that you have is something like this. You want to fill this corner in some universal way, right? It should fill the corner and it must be the greatest one, right? So you are actually pulling back this guy along this guy or this guy along that guy. So meaning that you are computing this, right? What is the computation set theory? It is just some specific version of product. So how to compute something like this, right? Let's say that we are in set theory, we have two functions, we want to compute this guy, right? How to do that? So I just compute x times z, all the pairs, and two projections, but that's bad because g of the y is not f of the x necessarily. So then I just restrict myself to them. So therefore, W is simply this. If you compute it in set, it is just x and z in x times z such that g of z is f of x. I'm just doing the obvious thing, right? Pick all of them and then just bring out the ones that make this guy commutative. And since it is all of them, then you have the greatest thing you can compute, right? So you can see, for instance, exercise that if you put one here, let's assume that you have terminal. And of course, then from anything to terminal, there is exactly one map by definition, right? And I write like this because I don't care about the name they are giving. So if you have the pullback of this along that, then you can see that the pullback is nothing but just the product. Simply, I'm saying that there is no condition because it is just a singleton, everything equals to everything. Okay. So this pullback guy is a very, 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 very important thing. And so if logically that guy is separation, this guy is substitution. Okay, that's weird, right? Is it really? So let's see. Let's come back to our U example. And let's say that this guy is just inclusion. And then we know that if we compute this, it is just simply f of f minus 1, right, of U. So then, let's see. So what I'm saying simply is that I have U, say, of y. It's my predicate. It's subset. And what is f minus 1 of U of x, right? When x is in f minus 1 U, exactly when f of x is in U. So the move is that you have this predicate, you want this predicate, you have the function f. You're substituting inside your predicate. Pullback is the categorical version of substitution. Okay. Yeah, yeah. For the general case. Exactly. Not really when we have these two. Exactly. So of course, when you have this, when you have that, you do exactly the trick, right? You produce the product in the categorical language and select out that part. So therefore, I can prove actually a theorem that you have pullback whenever you have equalizer and product. So you don't need it technically, but it is just a useful notion to have the name of it and use it here and there with some lemmas that I will explain, right? But it is not necessary. That's true. There is the dual version. The dual version is that I have two maps like this, and I push out, I fill this corner in the least possible way, meaning that I do this such that for any other guy, there is a unique map like this. What is a push out in set theory? Of course, it should be the dual of what needs it, right? So you add these two and quotient on the image coming from X on this relationship, right? Relation like this. So f of X is something like this. But f of X is g of y, right? So you put one copy and another copy as disjoint union, but then along the map, you do your billowing, right? And billowing is just a code. All of them are available in set, so some of them are redundant, so. And actually there is some other way to axiommatize it. So you can have pullback and one, the terminal, and then you can construct both of these guys. The product, as I explained in one exercise, but also this equivalent. So they are kind of equivalent, the pairs of one pullback and equalizer and product. Okay, fair enough. So now I have to say something. Come on, you see the general idea, right? I'm doing something again and again and again and again and again. The idea is simple. So what I'm doing is actually this. If you want to generalize all of them in one notion, you say that's what? You say that the general scheme is this. You have some object in your category, say A, B, C, I don't know, whatever. Some map, some commutativity, whatever, something. Right? And I call this guy a diagram for obvious reasons. Right? For instance, one diagram is this. Two separated points. One diagram is this. Nothing. The other is this. The other is this. The other is this. Right? These are my problems, kind of, right? And I want to find a solution for them. And a solution, there are actually two solutions somehow, right? You have a diagram. So you, in many of the examples that we had, terminal, product, equalizer, pullback, not to do all of them, just these guys. We want one object to gather morphisms to all the objects such that everything commutes. And the guy should be the greatest, meaning that so let's call this guy a cone over the diagram. So for any other cone, there should be one exactly morphism that, factors, right? So for any other cone, there should be one, right? Do you have it here, right? So what is a cone? The best cone is product. Here, what is a cone? When you have the empty thing. A cone is one object. A cone over the diagram, but there's no diagram, so just one object. such that that one object is the greatest, meaning that for any other object and the cone, which is again nothing, there exists one map. So simply I'm saying that there is one object. From any other object, there is exactly one map. So it's just the definition of terminal. Terminal is the limit. This guy is called the limit, the guy with the map of the diagram. So the empty, the limit is one. This diagram, the limit is product. This diagram, the limit is why? Because what is the cone? The cone is something here, let's say. One map here, such that you have the commutativity. When you say that you have the commutativity, simply you are saying that F composed with this is this, G composed with this is this. So you are saying that these two compositions are equal. And of course, this is redundant because you have the composition, right? Here, what's the cone? One guy, three morphisms, not two. Such that everything commutes. So this guy is redundant, of course. So, right? So all of them are limits of different diagrams. And in this case, diagrams are finite. Finite diagram is just a diagram when everything's finite, right? The number of morphisms and objects. So what I'm saying simply is that for some diagram, in set, you have limits. And I want it to be the same in my topos. The good news is that actually you have all possible limits in set. And what do I mean by that? So let's say that I have a diagram here, whatever it is, I don't care, right? It can be big, it must be set size, right? Not class size, that's the only thing. But it can be big, like what else? Like this. So let's say that A1, A2, A3, A4, etc., right? Infinite sequence, say, of objects, right? What is the limit of this? It is some object, projections, such that you have commutativity, but there is nothing. So it is just a product of all of these things. We have it, right? So all of these guys exist instead. And even better, they exist simply because product, the general product, not just binary that we saw, the general product exists and equalizer exists. Because as Neil told us, so the only idea to construct this guy, right, in any category with equalizer and product is simple. Just forget about this guy, right? So let's say that I have a diagram without any more some and I construct my product, right, with all the projections. But that is just too big because it does not respect these guys. So pick out via equalizer in some tricky way the parts that equal. So then if you have product and equalizer, you have all the limits, right? And if you have just finite product and equalizer, you have all finite limits for obviously.
So diagram does not have control?
It can. It can. It can. Yes.
None of your examples.
No, I didn't have. But it can be something like this. That's a good question. Right?
That could be the identity.
That could be the identity, which is yes. So if it is identity, you have just one node, nothing else. So the limit is itself.
How does that?
Yes, that's a good question. You can have it. Yes. So what is it? You want to see one example of it? Or? Sure. Okay. So
Because this statement is saying about.
yes, that's true also for these guys. But it is not that, of it. So I can complete it, of course, but I won't. So Okay. Yes, the dual of this guy is just colimit. You have a diagram. You want some guy such that every guy goes into it, and it is the least one. Meaning that for any other co-cone, you can factor it in a unique way. They are unique, of course, up to isomorphism up. And co-limit is just a dual of limit for obvious reasons. Push out, co-equalizer, co-product, initial, all of them are. So this guy, for instance, okay, this guy. What is the co-product? Some guy, two maps. It's co-product. What about this guy? Right? Some guy, two maps. It is here. It's co-equalizer. Not about this guy, because that is just nonsense. So the co-equalizer is C. So, but about this, of course, okay, three maps. Not one is redundant. Right? So now what I want to say simply is this. A topos is, I cannot define a topos now. I need more things. But a topos is a category such that there are three conditions. The condition one is that all finite, not all, just finite limits exist. Or equivalently, if you like, just the product exists and the equalizer exists.
I can just be a diagram to any pattern, yeah.
Any pattern that you can think of, right? As long as it is just finite. Right? So you have the best solution for all these problems. So, okay, then you may ask, okay, what happened to the co-limit and all the fuss, right? So we talked about the co-limit. That can be also an axiom, but since we have other axioms, we can derive that, the existence of all finite co-limits. But if you like, actually the original definition of Lavier had all finite co-limits as, right? All finite limits and all finite co-limits. So you have all these structures available in the topos, right? It is there in set, and you have it also in any topos. So, and I have to also say that if you have all finite limits, it's sure. No, no. I'm saying that from the existence of finite limits plus other things that the topos has, and I didn't explain yet, then you get all finite. But that's of course not true. Yes, that's the first. You need two other things. But before going there, and next time, maybe in the first 30 minutes, we will be there, then I can define that. I want to say that this idea of universality is the essence of categorical construction, right? So you have something, and that something is kind of a diagram. It could be in your category in these cases, or in other categories constructed from your category. It can be somewhere, right? And then you want to find the best solution of it. The least or the greatest, they are equivalent, right? So that's the idea. There are many ways to explain this. So some people define it equivalently via limits and co-limits, not necessarily in the category itself. It is equivalently, it can be equivalently described by something that's called adjunction. That's the fancy guy. And also via universal elements, so etc. Representability, I don't know. There are many ways, all of them are equivalent when you work with any category, right? But the point is that when everything is relative, when you want to define something, the only way to do it is just to work with the best, greatest or least, right? So there's no other way. That's not very surprising. The surprising part is that many, and I dare maybe to say that almost all notions that we use in mathematics are somehow of this sort. Because think about it, it is not obvious that Cartesian product can be defined as universal thing, but you can do it. it's not obvious that, I don't know, inverse image is, right? So we always work with the best solution. That's the thing. Therefore, we can define it via universal. And even better, the thing is that the other two are also the best solution of some problems, but not of the sort of limit. You can rephrase them as limits in some weird category, right? But they are not necessarily limits, right? So in the obvious category. So I can construct some word, some category, just similar to set theory, where you can develop the whole mathematics simply using the best solution to some problem, maybe three. That's kind of weird, right? And it explains something about the power of universe, right? That is somehow different from the usual set theoretical approach that you construct things from below, right? In a material way, you have this, you have empty, you have power set, you have blah, 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 you construct everything. Here, you don't construct things. You say, you describe things, but you axiomatize, their existence. You say that my problem, these problems, 1, 2, 3, 4, have the best solution to my category. That's your axiom, right? Since it is just seriously structural, because I'm not saying what is inside my sets, what are the elements, just the relationship between them via the morphism, then I'm allowed to find more and more structures, right? And in geometry, I don't know, in logic, in algebra, in whatever thing that you like. It's just kind of free in some very formal sensitive. Okay, so I guess I'm done for today. If there is any question, there is one. Sure. Yes. So the thing is that you get some equalities, right? But so many of them. Because any two edges with one map in the diagram, the composition should be equal. So you have so many equalities, you have to enforce them. So you go to the pi of some object again, and then you equalize all of them together, right? You can do it in Russia. Yeah. If you have the product, again, you use product to do it, because if you have two equalities, it is just one equality when you go to some appropriate product. That's the idea. Anything else? Yes. Yes.
So in my diagram, so when can I, just by looking at the diagram, how do I know which either one is going to because
That could be obvious, right? So okay. So let's see. So this one was the one that I explained, right? So let's say I have this, and then I said that there is no interesting really co-limit of this. Okay. So what is a co-limit? Yeah. Yes. But the point is that there is no condition really that you are putting. Or in other words, you have some sort of sink with no, commutativity.
But you want to also
Yeah.
but it is not.
But yes, because there is some equality. Yeah, I cannot characterize it graph theoretically, of course, right? I cannot characterize it graph theoretically that you can, I don't know actually, that if you see it, okay, that's kind of obvious. But if you just play it with 1 second, you see that, okay, there is no information, so it should be trivial. Okay. Time to pause. Okay. How to do this?